Okay, so far we've focused our attention on linear equations, except we did use some sums of squares back when we were looking at the x transpose times x, which recall is just the norm of x squared. So that gives you that sum of squares. Okay, now we're going to look at quadratic forms. Okay, and they occur in a lot of different applications, things like optimization, signal processing, physics, differential geometry, economics, statistics. So a lot of times you're going to end up with these quadratic forms. So let's look at how to handle those. So a quadratic form on Rn, so it's going to be a function on Rn that defines on Rn a value at a vector x that can be computed in this form. Okay, so the function's value can be gotten by taking a vector x, taking its transpose, times some matrix A, and then times the x itself. And so this is going to create this quadratic form. So the matrix A, in this case, will be a symmetric matrix, and it's called the matrix of the quadratic form. Okay, so a function that can be represented in this way as x transpose AX will be a quadratic form. So what we want to do is start with matrix A, and I want to show you how to get the equivalent quadratic form, that function. So we're going to start with x as x represented as x1 and x2, and we're just going to compute this value. So x transpose will be x1, x2 is a row vector, times the matrix A. In this first example, we'll have 4, 0, 0, 3, and then times the vector x. Okay, so I'm going to multiply these two together first, which is going to give me a 2 by 1, which will be 4x1, and then 3x2. Okay, and so this comes out to be 4x1 squared plus 3x2 squared. And this is our function, q of x, that you'd get that's in this form for that particular matrix A. Okay, so now let's find the quadratic form for this new matrix A. Okay, so q of x, x transpose AX. We're using x1, x2. Our matrix is going to be symmetric, and it's a 2 by 2. Okay, multiplying the last two together first, I get 3x1 minus 2x2, and minus 2x1 plus 7x2. Okay, so our q of x, okay, so row 1, column 1, so we're going to have one term. It's going to be x1 times 3x1 minus 2x2 plus x2 times minus 2x1 plus 7x2. 3x1 squared. I'm going to go ahead and get the squared term, so I'll have a plus 7x2 squared. And then I have minus 2x1 x2 and a minus 2x1 x2, so minus 4x1 x2. Okay, notice in this one that we actually had that cross product, the x1, x2 term, that we did not have in the previous one. This x1, x2, if you notice where it came from, it came as a result of this term times the x1 and this term times the x2. Okay, those values came from having those non-zeros off the main diagonal. Okay, versus over here we had zeros on the off the diagonal, so that we didn't have that cross product term. All we had was the squared terms. Also notice where these squared terms, the coefficients came from. They were just the entries on the main diagonal. Likewise here, the x1 squared was just the entry on in the first row, first column, and the 7 was the entry down in row 2, column 2. Okay, So now what I want to do is I want to go backwards. Given a quadratic form, can we find that matrix of the quadratic form? So here's the quadratic form, and we want to write it in this form right here. So we know that our vector x will be of the form x1, x2, x3. We're talking about x being an R3, and you see x1s, x2s, and x3s in the quadratic form. So there's our given x. Our matrix A, so just looking at the last example, we noticed that the squared term coefficients were in the main diagonal. So I'm going to have a 5 in the 1, 1 position, 3 in the 2, 2 position, and 2 in the 3, 3 position. Now this x1, x2 cross term, that's going to come from looking at row 1, column 2, and column 2, row 1. And because we want it to be a symmetric matrix, we're going to split that in half. So I'm going to put a minus 1/2 in row 1, column 2, and a minus 1/2 in row 2, column 1. Now this entry, row 2, column 3, will be half of that. So we're going to put 4 here, and then row 3, column 2, we're going to put a 4 here. Now there's not an x1, x3 term, so that means that you had to have had a 0 in the row 1, column 3, and column 3, row 1 position. So there's our matrix A. So if you calculate it out, x transpose A times x, this is what you'll get. Okay, so now let's see how we can actually calculate some of the values of this quadratic form. Now you can get those by just going through the multiplication. You know, if you just want to plug them in, here's your x1, x2. Okay, so q of x, where the x here is negative 3, 1, will be the x1 squared, so negative 3 squared, minus 8 times the negative 3 times the 1, minus the 5 times the 1 squared. So we'll have 9 plus 24 is 33, minus 5 is 28. Q of 2 negative 2 will be 2 squared, minus 8 times 2 times negative 2, minus 5 times negative 2 squared. So that'll be a 4 plus 32, so that's 36, minus 20 is 16. Okay, so the third example, we'll have 1 squared minus 8 times 1 times negative 3 minus 5 times negative 3 squared. So that's 1 plus 24, so there's 25, minus 45 is a negative 20. Okay, so let's just check this and make sure that we're going to get the same value as if we had used this form of the quadratic form. So I'd need the matrix A first. The matrix A, corresponding to this quadratic form, okay, we know it's a 2 by 2. Our main diagonal is going to be a 1 and a negative 5 with a negative 4 in the off diagonal positions. Okay, so there's our A. So that means this first one should be negative 3, 1. I'm doing x transpose times the A times the x. Okay, so the last two multiplied will give me a 2 by 1. I'll have negative 3 minus 4 is negative 7, and then 12 minus 5 is 7. 21 plus 7 is 28. And you see we did get the same answer here and here. So if you went through and did the same thing on the other, using these other two vectors, you would get the same value. So it's just a matter of which form you're using. Are you using the x transpose AX form, or are you actually using the more standard function form that we're used to seeing? So here's where you can really see it's a quadratic. Over here it's kind of hidden with the matrices.